All right, now, so far we found the electric field strengths. Started off with a long, thin rod. Check, no problem. Then we took that rod and made a loop out of it, so we made like a circular thing and then found the electric field straight above that loop. Nice. Then we took an arc of charge and we found what the electric field is someplace outside the arc, kind of symmetrical to the center. Check. Got ourselves a pretty good feel for that. All right, now we also have other shapes. So let's try looking at this. Now this is a disc. So think of it as a phonograph record or a CD or something like that. So the thing actually has a center to it. I mean, this thing is a flying saucer, like a frisbee. Okay, so this material, this is all filled in. So the question is, how do I find the electric field from this disc at point P? This one reminds me very much of the thin ring problem, where we had like a whole bunch of rings. So what we're going to do is start it out, do exactly the same thing we've been doing, and try to apply some of our old ideas to make it actually easier for us. All right, now we need to define a few things where we're going with this. So picture this phonograph record, and I'm going to cut that phonograph record into thin rings. Very much like the phonograph record itself. If you ever look, they have grooves in them. So the grooves are actually where a needle fits in, and then it spins around and makes the actual sound from the record. So what I've drawn is one of those rings in that center area. So picture this disc as a collection of individual rings, building out from the center, making it larger as I add more and more rings or more grooves in the record as I move out from where the label is. All right, now we define this as R. R is the distance from the center of the phonograph record or disc out to where the ring is that I'm looking at that moment. And big R is the distance from the center that the entire disc is. So this is big R, probably something that they're going to give you in the problem, how big the actual disc itself is. Now R is going to vary because it just depends on what ring we're looking at or what groove in the record as we walk our way out from the center. So our question, of course, is what is the electric field at point P due to this disk of charge? So that's kind of our setup. Now, what we're going to do is set this up, and I'd like to know, my first question is, how thick should I make the rings? So if I take a ring here, right there, how thick would be a good thickness for that ring as I built it out? Now be very careful, you know, as we walk away, aren't the rings going to get larger and larger as we walk away from the center? So they're going to vary. So when they change like that, don't I want to make small rings so that when I'm adding up the effects from each ring, I don't want one that's too wide because the inside of the ring and the outside of the ring are going to have two different properties to it. So these are going to be infinitely small rings, so I'm going to call these rings little DRs, like something along those lines. So each ring has a thickness of DR. All right, now, if we write down our basic formula here, all right, if we think about the electric field itself, we're going to have some issues with this. All right, now our first thing is, I'd like to know about our density. So what type of density should I use in this particular situation? Now we've been using linear density because we've been using things like wires or like real long thin rods or little hoops. All right, now this thing is actually filled in. My inclination is to use area density. So the area density symbol is sigma. So you might see that when you go to college, for example, above your sorority or fraternity house. So that's a sigma. And of course, sigma is the charge divided by the area. So if we look there, we take the area of the disk divided by the total charge, and that gives us our density. It's our charge density, and it's area density. All right, now, we know we don't want Q per se. We're going to want a dQ here. So if we take a look at this, and we have dQ, and then it's divided by the d area of that.